This is video number 2 for sections 2.3 and 2.4, the red cross problem. So this problem is different than the last one in a couple of ways. The first way is we're only going to be given 2 data points. And the second way is we are not given the variable definitions. You are going to have to define the variables. And when you're doing the homework, you'll see, all of these different types of problems. Here's the situation. Someone's interested in studying blood donation to the Red Cross. And so again, the idea, just like in all these problems, is somebody's collected some data, they've looked at it, and in this problem, somebody's done some preliminary work for us. They've already collected the data, they've already graphed it, they've decided that it fits a linear pattern, and they have decided that the 2 data points we should use are these 2 data points, that in 2009, people donated 6.6 million pints, and in 2012, people donated 5.9 million pints. Again, just from this brief sentence, you can see that the number has been going down. And so obviously, if someone's concerned about blood donation and the need for that, this would be something that they would be interested in. How do we turn this around? How do we change this trend? So they would want to study this. Well, if we're going to use modeling in the problem, we do have to come up with a couple of variables to measure, and we have to be very specific here. In other words, we kind of have to write our own let statement. Okay, I always need an independent variable, an x-type variable, and a dependent variable. So I go to my little sentence here and I say, well, what are we measuring? And of course, the obvious one is the pints of blood, right? Clearly, one of the things we're measuring is how much blood was being donated. What's the other thing? Well, it's a little more subtle, but of course, it's the time information. We also have time. We have years. So which is which? Well, this is where you think about that independent-dependent idea, right? What would make sense in this problem would be to say, well, the amount of blood donated depends on what year you're talking about. The passage of time for us has always been an independent variable. So I should use T or some other letter to stand for time, to stand for the independent variable, and then the pints of blood will be the dependent variable. Now we have to be specific. So what do we want T to stand for? Obviously some kind of years. We don't just generally write the year because I don't want to use these giant numbers in the problem. You may be thinking, well, let's pick a round year. Like let's say T stands for years since 2000. And I certainly understand the motivation there, but that is not the best way to go. The sentence up here says, listen, if you choose smart here, you can really make your work later on easier. The best way to go, if you have the choice, is whatever their starting year is, use it as your starting year. In other words, let T be the number of years since 2009. I'll show you as we go on why that turns out to be the best way to go. So T, number of years since 2009. How about we use B for the blood donation? How are we going to measure that? Well, it's being measured in pints, sort of. If I just say that, I'm going to have an awful lot of zeros at the end of my numbers. I'm going to say in millions so that I can use those small numbers that they gave me in the sentence. So B will stand for pints of blood given in millions of pints as they did in the sentence. Okay, now that we have those variable definitions, let's take the 2 data points that we have and write them as ordered pairs. So each data point corresponds to an ordered pair. Remember, the independent variable is T, the dependent variable is B, so these are T, comma B ordered pairs. Well, let's see, the first data point, we're talking about the year 2009. 2009 is 0 years from 2009, and in that year there were 6.6 million pints. So we've taken the sentence information and converted it to an ordered pair. The other one, let's see, 2012 is that year. That would be 3 years after 2009. And 5.9 million pints of blood that year. That's another T, comma, B. data point. This is so critical. Again, if you're going to use modeling, you need to have clear variables and be able to take the information and turn them into ordered pairs. Now that I have those, a lot of the rest of this is going to go pretty quickly. Next question. So what's the average rate of change? Well, we learned in the last problem that average rate of change is just another way to say slope. So they're basically just asking me to calculate the slope, the m. We know how to do that. We have a formula. So second y minus first y over second x minus first x. Let's see, I believe on the top there I have negative 0.7 and on the bottom 3. And so when I divide that out, I get about negative 0.23. I'm noticing there's no rounding instructions here. The homework, test, those will always be good about giving you rounding instructions. I just went to a couple of decimal places. And then the directions also say to include the units. So negative 0.23 what? Well, we talked about this in the last problem. Remember, the slope units are always a little bit complicated. It's one of those per things. You take your y units. Well, who's my y? Y is the dependent variable. That's the b in this problem. That's the pints of blood in millions. So this would be million pints. That would be on the top of the fraction, because that's what these numbers are. 5.9 million pints, 6.6 million pints. This negative 0.7 is million pints. And then per is the fraction bar. What are these numbers on the bottom? The 3, the 0. Those were years. Make that singular. And you've got it. The slope, or the average rate of change, negative 0.23 million pints per year. We're not asked here to write a meaning statement, but it would be very easy to do so. We would just say something like, well, blood donations to the Red Cross have been decreasing because of the negative sign by about 0.23 million pints per year, according to this study. Letter D. Now we want the equation of the linear model. Well, this is where our very smart decision up above is going to pay off for us. And this is why I'm telling you that if you have the choice to pick the starting year, you should use their starting year. Here's why. Look at the two data points I have. The one that should be really exciting to you right now is this one, because it starts with a 0, 0 comma whatever. 0 comma whatever, that's the y-intercept. That means I have it. I don't have to work for it. I don't have to do all that complicated stuff to find it. I have the slope and the y-intercept right now. That would not have happened if we had picked any other starting year. Like if you had said, well, I'll just use a nice round year like 2000. Then you'd have two data points here, but you would not have the y-intercept, and it would take you a lot longer to write the equation. So if you have the choice, you pick their starting year to be your starting year. Here's my equation. I don't have to do any work for it. I'll use x and y for the moment. Let's see. I have the slope, negative 0.23 x, and I have the y-intercept. It's 6.6. I can see it right here in this ordered pair. So there's my equation. Now, to use the correct letters, we had done b for our dependent variable, and we had done t for our independent variable. So that would be better. But then when I read the instructions, actually what they really wanted is they wanted function notation. So then in place of b, I'll have to replace that with f of, not x, but f of t would be my variable. And so here is the final answer to part D. There is an equation that sums up the information for this blood donation problem. Okay, let's just use it then to answer a couple of questions. First question, predict the amount of blood donated to the Red Cross this year. Now, this year depends on when you're watching this video. I am making this video in 2020, so I will use the year 2020. So how am I going to figure out a prediction for how much blood is donated in the year 2020? Well, it's all about those variable definitions. Let's see. So I go back up and I say, what were my variables again? What's the year information? Oh, yeah. T stands for years since 2009. So if I want to say something about 2020, I have to figure out how many years it's been since 2009. Just subtract, and you find that it's been 11 years. So 2020 minus 2009, our starting year, comes out to be 11. So to answer this question, I just need to calculate f of 11. Plug 11 in for t. There's not even much work to do. Just replace those t's with 11 and then grab the calculator and we'll have our answer. And I'm getting about 4.07 off the calculator. 4.07 what? What is this trying to say? Well, it's coming out of my function. The outputs of this function are the dependent variable values, which is the blood. This is not 4 pints, right? This is 4.07 million pints of blood. So we're saying that if that pattern continues where people are giving less blood at the same rate, then by the time you get to 2020, you're down to 4.07 million pints of blood donated. Okay, part F says, well, what if it keeps going down at that same rate? I mean, when is it going to go all the way down to where they're only receiving 2 million pints of blood? Okay, it must be after 2020. 2020, we're at 4 million. What about 2 million? Well, now, here's my equation that I'm going to use. Now I'm not plugging in a t because I don't know the year. I'm looking for the year. That's the question. Well, that means I must be plugging in a b, right? An f of t. Do I know something about the blood? Oh, yes, I do. It's 2 million pints. Now, this is tricky wording here. Don't write 2,000,000 because back up in our variable definitions, we said that the B actually stands for the pints in millions. So if you want to talk about 2 million pints, you would simply fill in a B value of 2. That means 2 million pints. So put a 2 where the B goes, and then you'll be solving this little equation for the T. And then, the math here is pretty much the same thing every time. I'll subtract 6.6 from both sides. And then I'm going to have to divide both sides by the negative 0.23 value to get that t by itself. And reaching for the calculator, this actually comes out nice. It actually comes out exactly 20. So the t is 20. Does that mean 2020? No, we already talked about 2020. To interpret this, I have to go back up to my let statement or my variable definitions and remember that, wait a minute, T stands for how many years it's been since the year 2009, right? That's how we started this problem. So 20 years after the year 2009 would be the year 2029. So we're basically saying, hey, if these patterns continue, then the Red Cross is going to be down to receiving just 2 million pints of blood by the year 2029. Is that going to happen? We have no idea. Maybe they'll change the way they're running things. Maybe they'll recruit more people in. Anything can happen, right? This is simply a prediction based on the trends that were provided in the original data that was collected.